Hi everyone, I'm Raghav, and in this video, we will discuss all the problems of today's Leetcode contest. In this contest, the first three problems were of medium difficulty, and the fourth problem was of hard difficulty. So, the very first problem is report spam message. The problem says that we have been given an array of strings message and an array of strings banned words, and we are being told that an array of words is considered spam if there are at least two words in it that exactly match with any word in the banned words in this array banned words, and we have to return true in case if the array message is spam, otherwise false. So it is like we have been given two arrays. Okay, let me change the size. Yeah, so we have been given two arrays of strings. The first array is message and the second array is banned words. So we have to tell if this message array is spam or not, spam or not. And the way in which we will decide whether an array is spam or not, uh, the logic for that is that if there is any array in which there are more than two words which are present in this array banned words, then this array would be spam. If there are at least two words such that this is happening. Let me take an example. So let's take this example. Um, yeah, okay, maybe I can change. Okay, so here is this example where we are having two arrays. The first one is message, and then we have banned words. So we are having the word hello, which is directly present in the banned words, and we are having the word world, which is also directly present in the banned words. So this message would be spam because we have got at least two words which are banned. And yeah, the answer is true. And in the second example, the word hello is not present, the word programming is present, and the word fun is also not present. So in this case, the message would not be spam, not spam. And here it is spam. Thus, the answer was true and then false, which matches with the expected output. So, I hope the problem is clear. The only thing which we have to do in this problem is find if there are greater than equal to two strings in message. Yeah, so we have to find out if there are greater than or equal to two number of strings in message which comes in the array band words. That's all we have to do. Now for doing this task, um, a simple approach is just count the number of strings which are coming up in the array band words. So count the number of bad strings. For now, I'm calling them as bad strings which are coming up in the array band words, or basically the if there are more than two band words. Okay, so for doing this task, one very simple approach can be that for each and every string, just go on throughout the complete array of banned words and check if there is any string which matches with this one. Then do the same thing for this, do the same thing for this, and so on. So it would be like for each and every word in the message, we would go through the complete string of banned words, the complete array of strings, banned words. Thus, the time complexity, let's say if the length of message is n, the number of strings in message is m, and the number of strings in banned words is m, then the time complexity will be big O of n into m multiplied with the maximum length of any word. So there will be this many comparisons, and in every comparison, the maximum length of the string can be 15. So uh, the time complexity for every comparison would be big O of 15. Thus, the total complexity will be big O of n into m into 15, which is not good because uh, the values of n and m can be as large as 10 raised to the power 5. Thus, this will give us a TLE, and we will have to do something more optimal. So we can do some pre-computation for this. Like this was the brute force approach which we have discussed, and the optimization in this case, in this type of scenario, is very standard. There are some data structures like sets, or even you can use a map or something. Though set does the exact same job which we need here. So basically, if you have studied about sets, you know that the main use case of set is to allow us to do three type of operations very efficiently. We can insert anything in big O of log n time. We can delete any element in big O of log n time, and we can find or basically check if some element is present or not inside the set in big O of log n time. This is what the set data structure can do, right? This is a prerequisite. Like you should know about this. You should know about sets. So how you could have thought about sets, the way in which you could have thought is, since for each and every character, for each and every character you sorry, for each and every string, you want to find if it is available in the second array or not. And for that you have been searching through the complete array. You are basically having big O of m time complexity for searching through the complete array, है ना? And in each and every comparison you are having a string of length uh, at max 15. So for each and every string you are having a time complexity of big O of m into 15 at max, right? uh, this searching part just to find out if something is available there or not. This thing should ring a bell in your mind that maybe you can use sets for optimizing this big O of m into 15 time complexity into big O of log m into 15 time complexity, right? uh, I hope you got some idea on how you could have thought about sets. This is the very general use case of sets, that we can improve our search time complexity. And the other use cases can, like you can think about them when you want a data structure which can insert elements and then delete from them, or insert elements then find some of the elements, like basically check if some element has been inserted or not in the set. So whenever you have requirement of such operations, you can think about the set data structure. So the approach can be like this. You had two arrays. The second one is banned words, and the first one is message. And we had a lot of strings in these arrays. So you can push all of these strings inside a set one by one. Just insert all these words in the set. This will take around big O of m log m time complexity. And since the maximum length of the strings is 15, so around this much time complexity, big O of m log m into 15. And you would have all of the band words inside the set. Let's call the set with the name band. After that, what you can do is go through all the words in the message one by one, and for each and every word, just check if this is present in the set or not. Um, you can check for each and every word in big O of log m into 15 time complexity. And since you have around n strings in the message, in this array with name message, so overall time complexity for checking out all the strings would be big O of n into log m into 15. So our overall time complexity becomes big O of uh, n plus m log m into 15. Right. Basically, add this time complexity and add this m complexity, and I took log m as common to just write it like this. Now the maximum value of n can be 10e5 and for m as well. Sorry, 1e5. So this part can be like 2e5. Log m for 2e5 can be around 18, 17, 18. And then this is 15. So it is gonna be 2e5 into 18 into 15 is around 270. So it goes like maybe 5e7. You can call it like this, which is good enough. Like we can have around 1e8 iterations, actually more than 1e8 in general. Uh, if we have a lot of constant factor, then around 1e8 iterations, and I think this is good enough. And yeah, I did code this and it did work out. I created a set of strings band, and I pushed all the words from the band words array into the set. After that, I created a variable with name band count, and then I went to each and every message inside the array of strings message. And if a word is present inside the band, like the set, in that case, I will increment the count. And at the end of the day, I want the count to be greater than 1, or you can say it as greater than equal to 2. Here, the time complexity is big O of n plus m into log m into 15. Okay. And by the way, in general, you won't really have uh, this 15. Like theoretically, we are multiplying the count 15 every time because the maximum length of the words can be 15. But in general, when you're comparing two strings, let's say you have two strings, string 1 and string 2. When you're comparing these two, you will first of all compare the first characters, then the second characters, then the third characters, and so on. So you would require 15 iterations for comparing two strings only when both of the strings are having the first 14 characters to be equal. So um, in general, that won't happen, I think. And like if that is happening, then the set would have a maximum length of 26 or something. So basically, I'm just trying to tell you that we have considered even worse than the worst possible case. In general, the actual time complexity or the actual time being taken should be a little less than what we have been considering. So I hope that this problem is clear, and let's move on to the next problem. This is the second problem. Minimum number of seconds to make mountain height 0. The problem tells us that there is an integer mountain height denoting the height of a mountain, and we have been given just wait 1 minute. Yeah, let's resume. So we have been given an integer array work times which represents the work time of workers in seconds, and the workers work simultaneously to reduce the height of the mountain. So it is like you have been given a mountain. There is a mountain with height, with the name mountain height, and there is an array. It is like you are having n workers, and for each and every worker, the time it requires, like for the ith worker, the time it requires is time I. And actually, it's not just time I; it's a bit different. They have actually told about this, that for the worker I, to decrease the mountain's height by x, it takes worker times I plus worker times I into 2, and so on till worker times I into x. So, oh yeah, by the way, instead of writing worker times every time, instead of that, I will write the word time, and instead of writing mountain height every time, I will write the word height. So we have n workers. For the ith worker, if he wants to reduce the height of the mountain by x amount, then the time it would require is gonna be equal to time I plus 2 into time I plus 3 into time I, plus like it will go on till x into time I. This is gonna be the time required by the ith worker if he reduces the height of the mountain by x amount. And obviously we can rewrite this expression as um, 1 plus 2 plus 3 and so on till x into time I. Since this thing is common everywhere, we have just taken it common, and then we are left up with the sum of the first x natural numbers, for which we know that the sum of the first x natural numbers must be equal to x into x plus 1 by 2. So this will be the time required by the ith worker to reduce the height of the mountain by x times, by the x amount. Okay, we have to return an integer representing the minimum number of seconds required for the workers to make the height of the mountain equal to 0. So we know that there are n workers who can work simultaneously, and their goal is to make this height become equal to 0. So let me take one example. If the height of the mountain is 4, let's say the height is equal to 4, and the times they require are 211, 211. So in this case, what we can do is, we are having three workers: worker 1, worker 2, and worker 3. We have to assign them some numbers, that how much height they should reduce from the mountain, such that the total height being reduced by these workers should be equal to height, so that the height of the mountain becomes equal to 0. And let's say we say that the worker 1 will reduce the height by 2, worker 2 will reduce the height by 1, and worker 3 will reduce the height by 1. Then in that case, the time required by worker 1 will be equal to, um, we can apply this formula, x into x plus 1 by 2 into time I. Since you want to reduce the height by 2, it would be x equal to 2, and the time required by the worker 1 is 2 as well. So time I is also 2 here. Thus we will have 2 into 2 plus 1, that is 3, by 2 multiplied with time I, that is also 2, and we have got the time required to be 6. Similarly, we will calculate the time which worker 2 and worker 3 require to reduce the heights by 1 and 1. So x is 1 and time I is 1 for them. Thus, the time they will require is going to be 1 into 2 by 2 into 1. That is 1 only. So, the total time required to remove the mountain, or basically, yeah, I think we can say the word to remove the mountain or make the height of the mountain equal to 0 is going to be equal to 6 because all of these workers are working simultaneously. So, the longest the total time required will be equal to 6 only because for the mountain worker 1 has been working for 6 seconds, let's say 6 seconds to make the height equal to 0. In the meanwhile worker 1 and worker 2 will also work, so the total time required would be only 6 seconds. Whereas let's say if worker 2, if it was something like worker 1 requires 6 seconds and worker 2 requires 9 seconds, then the total time required would be equal to 9 seconds. So I think you got the idea. The total time required by the workers would be equal to the maximum time required by any one of them. So our goal is to make sure that the maximum time required by any of the workers should be minimized. Right. This is our new goal. Now, for doing this, like obviously you can try to think of a few ways, but it can't be solved very easily because like whatever is this times array, when you iterate, like you can't do something like iterate over it and decide how much height should the ith worker reduce and how much height should the last worker or the last second worker should reduce. You can't decide it at the time of just iterating over the array, and you want to make the height of the mountain equal to 0. So it won't be very simple, and since it's not working out, like it won't work out when you will try it to find out the answer greedily, you will realize that you need to think of a different way of solving the problem. So let's try to think if we knew how much should be the maximum time, like how much should be the maximum time to be taken by any of the workers. Let's say I put up a time limit. Yeah, by the way, a reminder, we have already reduced the problem till this amount. Now I would highly recommend you people to pause the video here at this place and try at least 15-20 minutes for approaching the problem to solve the problem on your own. And in case if you're still not able to do it, that means you have already realized what I meant to say here, that the problem won't be very straightforward even at this point. Uh, and I will tell you how to approach from here. But first of all, you need to spend these 15-20 minutes. Otherwise, you won't really gain much from the problem, from solving the problem. You won't really gain much. So now I'm expecting that you have already spent 15-20 minutes at this place. And okay, just one more minute. Since elections are about to happen, there are a lot of rallies going on here and there. Uh, yeah. So basically, what we want to do is we want to find out the uh, minimum possible value for the max time. Right. We want to find out the minimum possible value for the maximum time taken by any of the workers. Basically, we have to do a min-max problem, min-max type problem. Some of you might have heard this name. Some of you might have not heard this name. This is basically a type of problem in which there is some information for each and every this. Okay, I think, yeah, one thing is that you should first of all try to search about this min max word, min max type of problems. And as the name suggests, we have to minimize the maximum. There is something, there is something, maybe there is an array. You do something on the array, and then you want that after you do something, whatever is the maximum value of the array should be minimized. If you ever have a problem like this one thing which should definitely come in your mind is binary search. That, can you try to put up a limit on the max value with the help of binary search? Can you put a time limit for the max value, maximum time required? Can you put up a limit on that? And then decide whether it is possible to solve, or basically, uh, is it possible that the maximum time required by any of the workers would be less than equal to max time? Sorry, time limit. Whether this thing can happen, and at the same time, the height of the mountain can go to zero. If both of these things can happen at the same time, then you know that the uh, time limit can be an answer. And we can just apply a binary search on this variable time limit. Let's say we had this as the time limit, which was equal to, let's say, 10, and right now I'm talking about a number scale. These are, let's say, the possible values for the time required by any of the workers. And we said that, hey, if I put up the time limit as 10, then all the workers will be able to work together and make the height of the mountain equal to 0. Then what I will do is I will say that, hey, 10 is my answer for now, and I will try to search in this range now, in this space, search space. Let's say I'm checking for 3, and I realize that, hey, the max time, if I keep the max time less than equal to time limit, which is 3 for now, then I could not make the height of the mountain equal to 0. In that case, I will search in this search space for the time limit to be greater than 4 and less than 10, and so on. This is how we just apply a binary search. So this is a type of min-max problem in which we are trying to minimize the maximum time, for which we have been putting up a limit on the maximum possible value, and we are checking if, while keeping the limit on the maximum value, can we make the height of the mountain equal to 0 or not. Now the question in your head would be, how will you check? How to check if the height of the mountain can become 0 while the time required by any of the workers is less than or equal to time limit. And there, okay, so this is the first question, how to check. And another question you should have is, uh, what should be the range for minimum and maximum possible, like minimum and maximum values where you need to search for time limit. What I generally do is I just keep the extreme values. And yeah, I will talk about this. There is one more thing you should have in your mind while thinking about binary search. The first question in your mind is that, is there a guarantee that if you can make the height of the mountain 0 in 20 seconds, then you can always make the height of the mountain equal to 0 in 21 seconds as well, 22 seconds as well, and so on. And if you cannot make the height of the mountain equal to 0 in 10 seconds, then you cannot make it 0 in 9 seconds either, in and you cannot make it 0 in 8 seconds, and so on. If this thing is a if this thing is true, only then you can apply the binary search, right? So first of all, we will think about this, and it's quite obvious that if you can make the height of the mountain equal to 0 in 20 seconds, Then you can use the same configuration for the workers to complete the uh, process of making the height equal to 0 of mountain in 20 seconds. So it can be done in within 21 seconds, within 22 seconds, and so on, right? And if you cannot make the height of the mountain equal to 0 within 10 seconds, and you can make the height of the mountain equal to 0 within 8 seconds, then there will be a contradiction, because you should be able to make the height of the mountain equal to 0 in 10 seconds also. And with the help of this contradiction, you can basically prove that if you can't make the height of the mountain equal to 0 within 10 seconds, then you cannot do the process for then you cannot do the process within 8 or 9 seconds either. I hope this is clear. I have explained this in a rush, because this is very common, but maybe I can explain it just so that in case if somebody didn't understand, then he will understand now. Okay, so I'm gonna explain this once again. First of all, we had understood that if the ith worker wants to reduce the height of the mountain in x seconds, then this is the total time required for that worker to reduce the height. And since all the workers would be working simultaneously, whatever is the maximum time required by any of the workers, uh, whatever is that maximum time required by any of the workers, uh, like this, in case if the workers were requiring 6 1 and 1 seconds for making the height of the mountain 0, then the total time required would be equal to 6, because these people are working simultaneously. So our goal was to reduce the max time required by any of the of the workers. We wanted to minimize this thing. We wanted to minimize the maximum time. So this is a very common type of problems. It is known as min-max problem, where we want to minimize the maximum thing. And if you ever notice a problem like this, you should always think about binary search. There can be more solutions for the problem, but binary search is a very common type of, like, generally these type of problems can be solved with binary search. So always think about binary search. Now, for verifying whether binary search can be applied for solving this problem or not, we need to think about a few things. The first thing is, if a problem can be solved, like if you can uh, make the height of the mountain equal to 0 in 10 seconds, then you should be able to make the height of the mountain equal to 0 within 11 seconds as well, within 12 seconds as well, within 13 seconds as well, and so on. So whatever function you will write to check if you can make the height of all the mountains equal to 0 within time limit or not, for that all of these people give yes, 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 right? And you would know that, hey, I can search on the left hand side now. And at the same time, this should also be true, that if the mountain cannot become with height equal to 0 in 4 seconds, then it cannot be made equal to uh, height, like the height of the mountain cannot become equal to 0 within 3 seconds or within 2 seconds or within 1 second. This should also be true. So if you ever check for the time limit 3 and you get a no, you would know that you have to search on the right hand side now. And we know that this thing will obviously happen, because if you can make the height of the mountain equal to 0 within 10 seconds, then obviously you can make it within 11 seconds as well, within 12 seconds as well, within 13 seconds as well. Let's say you were able to make the height of the mountain equal to 0 within 8 seconds, then 8 seconds is less than 10, 8 is less than 11, 8 is less than 12. So yeah, we can say that we would be able to make the height of the mountain equal to 0 within 11 seconds as well, within 12 seconds, within 13 seconds, and so on. And if you cannot make the height of the mountain equal to 0 within 4 seconds, like you want that if for time limit equal to 4, if you got a no, then you should get a no for time limit equal to 2 as well, right? You want this, that if this happened, then for time limit equal to 2 as well, you should get a no. Now for proving that it would always be true, you can just assume that, hey, let's say for time limit equal to 4 you got a no, and for time limit equal to 2 you got a yes. Then it means that it is possible to make the height of the mountain equal to 0 in less than equal to 2 seconds. That means that it is possible to make the height of the mountain equal to 0 in less than equal to 4 seconds as well, which means that for time limit equal to 4, the answer should have been yes, but we know that the answer is no here. So it makes sense that we are having a contradiction, and um the time limit, like the answer for time limit 2 cannot be yes, it must be no if the time limit for 4 is no. So this is how I prove whenever I have to confirm if I can apply binary search or not. The second thing is, how will you check? How to check for a particular time limit? What you want to check for a particular time limit is that you should have the max time always being less than equal to time limit, and you should be able to make the height of the mountain become 0. This is what you have to check. And the third thing you need to think is, what should be the range in which you check for that uh, value of time limit. Basically, what would be the starting range and what would be the ending range for binary search? So yeah, you can try to think of some exact values, like if you have the height equal to 10 and the maximum time required by any of the like basically the maximum value of the times array is 4, then you can just assume that the like you can always make the height of the mountain equal to 0 um, in 220 seconds. So your binary search, the ending range of the binary search should be equal to 220 in this case, right? And the starting range, uh, you can try to think of a value for that as well, though it would be a bit tricky. But in general, I say, in general, what I do prefer is always keep the start and end point as extreme points, like 0 and 1 8, something like this. In that case, I don't really need to figure out what can be the maximum time required by the workers to make the height of the mountain equal to 0 or 0, right? So in a nutshell, in the third point, what I have discussed is you need to figure out the start and end points. In my case, what I did is I just kept them as 0 and 118. The reason it would still work is because you know that on the right hand side you are always having yes, 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 right? So having a very large value for end as well, end won't really affect your question, like it won't really affect your answer. And on the left hand side, as you reduce the value of time limit, your answer will just go no, no, no. So you just need to make sure that the actual answer which would lie, like the actual answer should lie within this range from 0 to 118. So you need to make sure that whatever is the maximum time required for making the height of the mountain 0 should be less than or equal to 118, and the minimum time, like that time, the minimum, again I should say that the minimum possible value for max time, this value should definitely come to be greater than equal to 0 and less than equal to 118. Right. Now you know that the height of the mountain would be at least 1. So obviously the minimum time required for making the height 0 would be always greater than 0. So this is not a problem. Like the start value is definitely not a problem. And you need to make sure that the time you require should always be less than 118 in all the cases. So even in the worst case, the maximum time you would require is gonna be in a case when the mountain's height is equal to 1e5. When the height is 1e5, there is only one worker, n is equal to 1, and the time required by that worker in the basically the time array is having 1e4. This is gonna be the worst case where you require the maximum amount of time. So here it would go like this is the x value because we will have to reduce the height of the complete mountain by this single worker. So we can apply the formula here, x into x plus 1 by 2 into times of 0. Thus it goes like 1e5 into 1e5 plus 1 by 2 into 1e4, and this value would be less than 1e14, right? This would be less than 1e14 because 1e5 into 1e5 would be around 1e10 by 2 into 1e14 1e4, so it should be around 1e14 by 2, a little greater than this, and we are taking 1e14 as a like upper limit. And yeah, in our case, like in my case, I just took 1e18. I knew that uh, whatever value I will have around 1e12, 1e14, 1e16, whatever would definitely be less than 1e18. So I did save some time while solving the problem because I didn't really have to think of the worst case as I had already taken a very very big value. But you can take anything, like you can take anything for end value to be 1e14 or greater than that, or just apply this formula of x into x plus 1 by 2 into either time of 0 or minimum of time, maximum of time, whatever, because everything will work. Okay, so we have figured out the minimum and maximum possible values. We know that binary search will work. Now the third thing which we have to do is how to check whether for a particular time limit we can make the height of the mountain equal to 0 or not. So it would be like you would know about the time limit, you know about the times required by all the workers, and you know about the height of the mountain. So this part is pretty straightforward. This part is like very straightforward because for each and every worker now you have some time limit. So you can just say that, hey, um, whatever is the maximum height I can reduce, whatever is the max height, like we are talking about the ith worker. For the worker I, how will we know how much height he should reduce? So for that we can just say that for worker I, the maximum height or the maximum x it can reduce from height it can reduce from height such that x into x plus 1 by 2 into time of I should be less than or equal to time limit. Right, that's all I care about. If I just make sure that for each and every worker the time it requires to reduce the height of the mountain is always less than or equal to time limit, in that case I will be able to make sure that the maximum height of the mountain would also be less than equal to time limit. And since I want to reduce the height of the mountain by 0, or actually I need to figure out if I can reduce the height of the mountain by 0, I can just find out the maximum height each and every worker can reduce while taking time less than equal to time limit. So I will be able to figure out the maximum height which the workers can reduce from the mountain within the time limit. Let's say I got the total height which the workers can reduce as total height. I'm just calling it as total height, which the workers can reduce. Then I can just say that if this value is greater than or equal to height of the mountain, actual height of the mountain, then my answer is yes for the time limit, else my answer is no. Again, I think this is not a complicated thing. And how will you find out this maximum value of x? So all you want to do is you just want to find out the maximum value of x here. Like you have this equation x into x plus 1 by 2 into time of I being less than equal to time limit, and here you want to find out the maximum value of x, right? um, Maybe you can try to uh, manipulate the equation a little bit, maybe keeping the like taking out this 2 at this place and taking this time at the denominator on the other side, and then think that you have got this. Basically, you're having a quadratic equation and you want to find out the maximum value for x here, है ना? And you can do try out a few things, but I don't think anything will work out other than binary search here. Like eventually, you would require to use binary search, as far as I can think, for finding out the max value. And yeah, this one is a very standard problem. Like earlier as well, I had pointed out that as soon as we notice this min max thing, we should have thought about binary search. Similarly, here as well, whenever you have some expression and you want to find out the minimum or maximum possible value for a variable, and this is the only variable in this equation. Like time I is not a variable, you would know about its value, and you know about the value for time limit as well, and you want to find out the maximum possible value of x. This is the only variable in the equation. Then you can always apply binary search. Let me point out a very standard problem, which is x square to be, basically you are being given a number, given an integer num, and you have to find out the square root of num. This is a standard problem which I believe many of you would have already seen. It is uh, this problem is present in almost all the DSS sheets you see, including Striver A to Z sheet or Lovebird sheet. This would be present everywhere, even in the sheet of Apna college. So I would highly urge you to go and try out this problem, in which you have to find out the square root of a number. Basically, you can just search the problem square root of a number using binary search. Just search this thing online and you should definitely be able to find the problem. Maybe I can search it. Binary square root of a number using binary search. Uh, yeah, you can find out the problems. Like the problem is here in Geeks for Geeks here, and even on the website of Take You Forward, you are having this problem. And yeah, it is present even on Leetcode. So you can find out a lot of places where this problem is available, and at each and every place you will find a lot of solutions as well. So let's say you can't solve this problem on your own, and you want some solution, you would find them online. So go and solve that problem first, then come back to the problem. you would already be good enough to figure out how to find out the max value of x from this equation. So yeah, for a given time limit, you can apply a binary search to find out the maximum possible value of x for each and every worker and find its sum to get the value of total height, and then you can just uh, say that total height should be greater than equal to height, otherwise you will say no, otherwise you will return no. So that's it for the problem. Let me show you the code. I know the problem solution got a bit lengthy, so some of you might have got confused at some place or might have forgotten what we had discussed earlier. So this is the time. Just pause the video, and try to think about the solution on your own now. Always remember that the more efforts you put by your own, the better it would be. Just watching the video won't be enough. So here is my code. The code is pretty short. Um, yeah, maybe I can even reduce this and write it like this. Okay, so in the code we are applying a binary search here where the starting range is taken as 0 and the ending range is taken as 118. Feel free to use your own ranges. Just make sure that their answer is coming up within this range. Initially, I initialize the answer with the largest value. So here in the binary search, I'm trying to figure out uh, the minimum possible value, or basically, I'm trying to minimize the maximum time taken by any of the. Yeah, I'm trying to figure out the minimum possible value for max time. So for each and every middle guy, like you will just calculate the middle guy like this, and then you will try to check if this middle, like if this is the time limit here, m, I've used the word m here. Basically, this is the time limit, and here this is the mid. Instead of mid, I have just written it as m because during the contest, I wanted to just write as short code as possible. So this is the time limit which we had. Yeah, for each and every worker, yeah, maybe I can just make a little bit of change in the code so that it matches with what we had discussed in the explanation. Total height can be written as 0, and you would want the total height to be greater than equal to height. This is the height which you can reduce, and this total height variable would increase every time. And this is the time limit. So what I'm doing is, for each and every worker, I'm finding out the maximum number of the maximum height which this worker can reduce within the time limit, and then for figuring out the maximum height the uh, worker can reduce within the time limit, I have been applying a binary search here to figure out the largest possible value such that the sum of like the okay in the binary search, I'm trying to figure out uh, the largest possible value, or basically the maximum height the worker can reduce within time limit, and the time it requires here is less than, let's say, equal to n num. So you know that Here the range for the binary search can be taken from 0 to 1e5 because your answer would never be less than 0. It cannot be negative. You cannot reduce the height in negative, and uh, you cannot reduce the height of the mountain more than 1e5. So I took the upper range as 1e5. And let's say here m is the amount of height you want to reduce from the mountain, then the time required by this worker to reduce the height of the mountain by m would be equal to m into m plus 1 by 2 into num, right? Here instead of x we are just having the variable with name m, and num is the time required by the ith worker. So this should work. So you can just write time required to be less than equal to time limit. And yeah, I think that this code should be understandable now. Though I do not recommend you to look much at my code, I do recommend that you should try to write the code on your own, and try to avoid looking at my code as much as possible. It's a good habit to uh, put up more efforts by yourself. Now let's try to think about the time complexity for the problem. Um, First of all, we are having a binary search. This loop will go on around the go of log of 18 times, which is around 60. This loop will go around 60 times here. Inside the while loop, I am calling this check function again and again. The check function will have a for loop inside of it, which will go on around time dot size again and again. Let's say the size of the time array is n. So this for loop would like this for loop is having n iterations, and the function would be called around 60 times. So we are having 60 into n times this find function being called find max times, and the find max function is having another while loop which will have log of 1e5 iterations here. So it will have log of 1e5 iterations, which is around 18, 17, 18. So the overall time complexity for this function has gone like 1080, sorry, yeah, 60 into 18, that is 1080. We are having around this much time being taken, and the value of n here is uh, as large as 1e4. So this is as large as 1e4. So the overall time complexity would be like overall iterations would be around 1e7, which is good enough. There will be no problem of TLE here. And the space which we have required is, yeah, we have not created any extra vector or array on anything. So the space we require is gonna be like just constant. It would be the space complexity would be big of 1. So yeah, let's move on to the next problem. This problem is, I think, simple for being a C problem. The problem says that there are two strings being given to us, word 1 and word 2. So we have been given two strings, string 1, string 2. They are having the names word 1 and word 2. And we are being told that a string x is called valid if x can be rearranged to have word 2 as a prefix. So we call a string to be valid. Uh, we call a string to be valid let's say for a string x, if we can rearrange the string so that after rearrangement, let's say the string was AABC and the word to here is maybe BA. If you rearrange this string and you can make sure that the word to is coming as a prefix in the string x after rearrangement, then the string would be called as a valid string. And we have to tell the total number of valid substrings in word 1. The aim is to find out total number of valid substrings in word 1. This is the goal. Okay, so the first thing which I want to say here is just for the sake of explanation, instead of calling the word 1, like I would call the string as string str, and I will call this string as target string, which I want to be coming up as a prefix. And instead of calling the string as valid, I will call this as a good string. So our goal is to find out how many good strings. Sorry. So now I've just changed the names of the variables. That's it. So now I'm calling that I want to find out the count of good substrings in in string str. And what I mean by good substring is um, there, like by good substring I mean that it should be a string coming as, or basically it should be a substring of str and it should be good. So any string which is a substring of str and it is good would be considered as a good substring. I hope it's fine. I mean, I hope that the problem is clear. So one way of solving the problem. Okay, first of all, we need to understand how will we verify if a substring is good or not, or if a string is good or not. Let's say you are being given two strings, um, s1 and s2. How will you verify if s1 is good or not and if s2 is good or not? Where you just need to verify that after making some rearrangements in the string s1, if let's say we call the string after rearrangement as s1 dash, it should have the target string as a prefix. If this thing is possible or not, how will you verify? So for this, uh, one simple observation is, one simple way can be to find out all the permutations of s1 and check if any of the permutations has a target as a prefix. Just check out this thing. But it would be very inefficient. Finding out all the permutations will take around big O of n factorial time, where n is the length of the string. So we need to think of some better way. Now tell me one thing. If let's say you have a string AABC and the target is equal to Z, is it possible in any case where you rearrange the string such that the first character is equal to z? Obviously, it's not possible if the string s is equal to this and the target is z. So what we have noticed now is, yeah, the strings are like this. So what we have noticed is, if target is having any character which is not available in the string s, then the answer is never possible. At the same time, let's say if target was equal to, like instead of being equal to z, if the target was equal to bb, would it be possible to make the string s um, be arranged in a way that the first two characters are bb? Again, the answer is no. It's not possible. Why? Because the frequency of b coming up in target is greater than the frequency of b in the string s. So yeah, we can say at least one thing, that the frequency of each and every character in string s should be greater than or equal to uh, that in target. The frequency of every character in string s should be greater than the frequency of that character in string target. This thing should definitely hold, otherwise we know that the string s cannot be good. Now, can there be a case where this condition holds up but the string is not good? Try to think about it. Maybe pause the video and try to think of a counter test case where the frequency of each and every character in string s is greater than the frequency of that character in string target, and yet we are not able to rearrange the string s in any way such that the prefix is equal to target. I hope you tried and you would have not been able to figure out any such case where this condition holds but the string s is not good. And the logic is simple. Let's say there is a string a b b c c d, and this is string s, and target is equal to cbad, anything such that every character is coming up less than or equal to the number of times it is coming up in the string s. Then out of all the permutations of string s, there will definitely be a permutation in in which the first character is equal to c, the next character is equal to b, the next character is equal to d, and the next character is equal to d, like cbad. These are the first four characters in string s. There must be a permutation, and then you don't really care about the rest of the characters. There can be too many permutations in which this is coming up as a prefix, um, and there can be some permutations for these people as well. But you don't really care about the other people. You just know that if this condition is holding up, then there will definitely be a permutation of s such that this thing comes up as a prefix. So now we know, like we can just create a function is good in which we pass on vector of int count and vector of int required count or target count. These are the parameters in the function with name is good, which will return true if count of, like this very vector of integers count will actually keep track of the frequency of each and every character in the string s, in the um, string which we want to check if it is good or not. And this required count, this vector of integer will keep track of the frequency of each and every character in the target string. Maybe we can call it as target count as well. The string is target count. So it will return true if count of I is greater than or equal to target count of I for all I belonging to the range from 0 to 25. Basically, for the alphabets from A, B, sorry, yeah, for all the alphabets from A, B till Z, you can just store their frequencies in count of 0, count of 1, and so on till count of 25. This is a very common practice. So you can create such vector of integers, and then um, the function is good will return true if the frequency of every character in the count array, basically the frequency of each character in the string s, is greater than or equal to the frequency of each character in the target string. Otherwise, it will return false. Right. So it would be a good thing. Right. In this way, we would be able to check if a string is good or not in just big O of 26 time complexity, where we already have this count array and this target count array. Now, some of you might be thinking that, hey, when we created this is good function, we could have passed on the two strings itself, string s and string target. And yeah, you're right, you could have passed this. The only problem is, then this function would calculate the frequency of this target string again and again. And every time you call this is good function, it will iterate over the target string and calculate this target count. Right. So it will just um, cause big O of m time complexity, where m is the size of the string target, for just calculating this target count, whereas you can just calculate it once and then pass it into the is good function if you are having the is good function like this. Similarly, for the other string s, if you had to like call this function only once, then it is good to have the function in this way. But since we know that we would be calling the function many times, and every time the string which we pass on won't really differ a lot. Like we are having substrings, we have to call the function for all the substrings, right? So once I will have this as the substring, then in future I might be having this as the substring, then I might have this as the substring, then this, and so on. So the frequencies of those substrings, or actually those substrings, won't differ a lot. So we can make some optimizations, like if we know about the frequency of all the characters in this substring, once I've called this function, I don't really care about the substring anymore. So I can just remove the first character and maybe add one extra character to be able to get the frequency of all the characters in this substring, and so on. I can make some optimizations in future. That is why creating the function like this would be better. But if you're not satisfied, then just think of creating the function like this one for now. And in future, we will see that for optimizing this problem, we will have to come up like this. Okay, so now the idea is in the string of length n, there will be n into n plus 1 by 2 number of substrings. There will be this many substrings. If you have created a function like this one, where you are passing both the strings and then the frequencies of all the characters in those strings are being calculated, and then the comparison happens, then this is good function will work in big O of n plus m time, where, or maybe n dash plus m time, where n dash is the frequency, n dash is the length of the string which you are willing to check if it is good or not, and m is the length of the target string. So you can call this function for all the substrings. Thus, your time complexity would be around n into n plus 1 by 2 into n dash plus m. And in the worst case, this n dash can be equal to n. है ना? In the worst case, you are taking the complete string. So this n dash can be treated as n for the worst case. Thus, you are having a time complexity in order of n cube m, big of n cube m, which is very, very bad. You need to optimize it. Then there comes the idea that hey, I can go in a way like this. As I checked for this substring, and when I want to check for the next substring, in the isGood function, instead of calculating the frequency of all the characters again, I will just keep track of vector of integers count by myself and will increment the frequency uh, of the character available, basically present here. And then I will pass on this vector of integer count and vector of integer um, target count, which I could have calculated in big of m time complexity once. And then I will just pass on these two functions again and again to the isGood function. So I won't really have to calculate the frequencies of the characters inside the function. Thus, this function would work in big of 26 time. So we can optimize a time complexity to something like 26 into n plus 1 by 2, but it is still too bad, right? And we need to optimize the solution even further. um okay, since this is a recorded video, I'm not 100% sure if everyone would be able to understand till this part or not, but we have not really done any hard thing till now. We just made one good observation. This is a good observation which can help us to figure out whether a string is good or not. Then for checking whether a string is good or not, you could create a function which we will call again and again. But in that function, if you calculate the target count and the count again and again, then the solution was very inefficient. Let me take an example. Let's say you had uh, there is a substring of length 1e4 for which you had called the function. Let's say you had called the function for this substring of length 1e4, and then you call a function, like you call the function once again for the substring in which you have just added one more character, and the substring is of length 1e4 plus 1 now. So if that is good function took on 1e4 iterations to calculate the frequency of this substring, and then it takes 1e4 plus 1 iterations for counting the frequency of this substring, then it is just too inefficient, right? We are just doing the part till this point once again, which is not good for us. So this is why we would tend to keep track of the frequency till this part, then add this character again, like add this new character to the count array. After that, just pass down this count array by reference to the function and do this part again and again. Like you will add one more character and then pass on this count array again, and so on. In this way, we will be able to get the answer very efficiently in just big of 26 time for every function call. Okay, again there is a rally. Not really a rally, but promotion. Okay, nice. It's still there. Let's wait for a minute and let this car go on. Okay, nice. It has gone now. Okay, so now the problem is we have been able to think about a way for checking whether a string is good or not in big of 26 time complexity where we know about the frequency of all characters in the string. And since there are a lot of substrings for which we have to call this function, the overall time complexity was going up to n into n plus 1 by 2 into 26, which is very bad. Now let me share um, a tip from my experience. Whenever you have something to do with a lot of substrings, you want to check something for all of the substrings, and you want to count the total number of substrings which count of total, or basically you want to find the total number of substrings which satisfy a function. And inside that, uh, basically you have to do something for all the substrings. Then a lot of times those problems can be solved by using prefix sum arrays, basically for substrings or subarrays. If the problems are related to that, then a lot of times those problems can be solved using prefix sum arrays or binary search with prefix sum arrays, binary search and prefix sum arrays. And the third possible way is sliding window. Generally the problems can be solved in one of these three ways. The sliding window, I'm just talking about two pointers here. The sliding window might be static or it might be dynamic. It might be a dynamic sliding window or static sliding window. Both of them are possible. uh, Generally the sliding window would be dynamic, not static in this case. uh, Anyways, we will just think of the problem as two pointer problem. Nope, there is that's not a big deal. So since you will have something to do with the count of characters, a lot of times you will require the count array a lot of times for the uh, subarray substrings. So I always believe it to be a good thing to just create a prefixum array for the uh, we can always create a prefixum array for the substring for the string where prefix of 10 4, something like this, or maybe you can call it as prefix of I, comma j, will tell me the number of occurrences of jth character this jth character is the jth alphabet, basically jth alphabet. If j is equal to 2, then I am talking about the character c. If j equal to 0, then I am talking about the character a. If j is equal to 25, then I am talking about the character z, in this way. So the occurrences of that jth alphabet among the first I characters in the string s. I can create a prefix some array like this one. where prefix of I comma j is storing this information. The number of times the jth alphabet has come among the first I characters in the string. So for a substring from index L to R in zero based indexing, if I want to find out how many times the character um, G came up, then I can just get this information from prefix of R plus 1, since this R is in zero based indexing, but um, this prefix sum array which I've created is in one based indexing. So I will just say prefix of R plus 1 in the other bracket, like this G would be having the index 6, I think. Um, as I was representing A as 0, B as 1, I would represent E as 4 and F as 5 and G as 6. So prefix of R plus 1, 6 minus prefix of L 6. This thing will tell me about the number of times 6 has come in the in the substring from L to R. So creating this prefix summary won't really be a big problem. Generally, the memory limit is big enough that uh, creating a prefix sum, like you know that you have an array of length and you would be mm, making some operations, you would be using some operation. Um, yeah, basically you are having an array of size n is not too huge, and generally n into 26 would also be not too huge. So since in our case n is less than equal to 25, n is less than equal to 25, we can create this prefix sum array. It might help us, and in case if it does not help us, then we can just avoid using it. है ना? Like we can just uh, avoid the part of creating it in case if we don't really use it. But for now, let's consider that we have a prefix sum array with us for helping us. And then there was one observation. Again, this is something used a lot of times when you are having problems related to finding the total number of, whenever you have a problem related to finding the total number of substrings. Many of those problems can be solved in this way, where you just try to identify that, hey, if this string, if this substring is good, then either you are thinking that all of these substrings would also be good. If you can, uh, like if this thing is true, like if I say that a substring, if a string ABCCD or ABCD, AABCD is good, can I say that the substring AAB would also be good? Can I say this? In case if I can always say that if a substring AABCD, which was coming here, is good, then all the substrings which are contained inside the substring would also be good. If I can say this thing, or if I can say that all the prefix of this substring would also be good, in that case I can always optimize the problem. I can always optimize my solution. But in this case, there is no guarantee. If this substring is good, a prefix of this substring might be good or it might not be good. है ना? Like in this case, if the target string was AB, then yeah, this substring is good. But if the target was something like, let's say, BC, then this would not be good, right? So we can't optimize the solution in this way. Let's try to think of the other way then. If I know that a substring is good, then can I say that all the substrings for which this substring is, like all the substrings for which this particular substring was coming as a prefix would also be good? Basically, if my substring was A, B, C, D, and the next character is E, and let's say then there is F. Can I say that if A, B, C, D is good, then A, B, C, D, E, F must also be good? Can I say this thing? Because if I can say this thing, in that case, once I know that this substring is good, I would not look up for all of the substrings which are having this as a prefix. So basically, I will save a lot of time because I can avoid a lot of substrings, right? And in this case, we can say that yeah, this would also always be true because whatever substring is having this current substring as a prefix, it means that all of the characters which were present in the substring, let's say S1, would also be present in the second in the bigger string S2. So yeah, we can optimize the problem. Um, some of you might not have ever solved the problem by optimizing in this way. It might be the first time for you, and congratulations then, because you got to learn about a new thing. You will get to learn about a new way of optimization. So now the idea is for like this was your main string str. You know about the target count because you know about the target string, so you could have calculated the target count. You don't really care about the target string anymore. You only care about the target count because that's all what mattered. Now for any string, let's say this one, if you figure out that this is good, then in that case you will not check for this substring or for this substring or for this substring or any of them. You just know that all of them must be good. So if the substring was from index L till index R, you know that the substring from index L to R, from L to R plus 1, from L to R plus 2, from L to R plus 3, and so on till from L to n minus 1, all of them must be good, right? All of them must be good. So you can just skip all the other comparisons for all of them. You can just avoid them, and you can like whatever variable you would maintain to keep track of the number of good substrings till now. Let's say this is a variable answer. In this answer substring, sorry, in this answer variable, you can just add the number of good substrings you have found. This is nothing but all the substrings which were ending from ending on R till all the substrings which were ending on n minus 1. So this is nothing but n minus 1 minus R plus 1. That is the number of that is the number of uh, integers coming up in the range from R to n minus 1. The number of integers here, that is gonna be nothing but n minus R, sorry, n minus 1 minus R plus 1, uh, which becomes n minus R, right? So you can just say that every time you find a good substring, you will add n minus R to it. And now you know that for all the substrings which are starting from L, you don't really need to uh, check for any of the substrings which are ending at this place. But what about the substrings like this? What about a substring like this one? We don't really know if it can be good or not, right? We don't really know if it can be good or not. So if we just randomly check for any R, it won't be good enough for us. So what we should ideally do is for each and every L, try to find out the first value of R such that the substring L to R is good, whereas the substring from L to R minus 1 should not be good. In that case, like if you know that this substring is good and this substring which is ending on r minus 1 is not good, then you know that this substring, all of these would be bad, and this substring, including this current substring as well, all of these will be good. So in this case, you can just simply add answer plus equal to n minus r and then check for the next value of L and so on. I hope this looks good. Um, I don't really know about the count, but I have solved too many problems in which the solution was in this exact same way, where we optimize the problem to a way that for each and every L, I am either trying to figure out the largest value of R. That happens in the case when I know that if this is a good string, then if this is a good substring, then all of these substrings would also be good. If I know about this thing, then I will try to find out the rightmost value of R. Otherwise, I will try to find out the leftmost value of R, where I know that this substring, and so on. All of these substrings would be good. And in this case, I will just add n minus r to L, and then I will check for the next value of L, and so on. And for finding out the leftmost value of R, I can apply a binary search. Now, while applying binary search, and like when I'm applying a binary search, since I want to find out the frequency of all the characters in this substring, I would require the prefix sum array here. The prefix sum array would be required at this place. And yeah, that's it. So uh, I believe the problem should be doable now. For every L value, you know that the R value would either be from this place, like the R value would at least be this, and it would at max be this. Just try to figure out the leftmost possible value of R where you are having the string L2R being good. So this is R min, this is R max, and yeah, this is completely possible that even for R max, the substring is not good. Like it is possible that even in the substring from L to R max, which is nothing but R minus n minus 1, is not good. In that case, you don't add anything. In that case, you won't add anything. So what I did in my case was I just said that the R value was initialized by n, and in the binary search, whenever I find out any place where L2 R mid, like this would be the R mid initially, and I will check out multiple R mid values. So whenever I find out that L2 R mid is good, I will say R equal to R mid, and then R max equal to R mid minus 1. So basically, uh, this thing will come out to be at this place, and R will become equal to R mid, and the search will go on as long as R min is less than equal to R max. And let's say in case if none of the R mid would have satisfied the condition, then my value of R would have never changed and it would have been equal to n. So at the end of the day, when I'm adding n minus r would be equal to n, so answer won't be incremented by anything. Now it's up to you if you want to use if else conditions even at this place. It's fine. The implementation can vary person to person. So the time complexity here will be what did we do? First of all, we calculated the target count. it will take big O of m time. Actually, big O of m into 26, or yeah, just big O of m, big O of m, nothing else. And we calculated the prefix sum array, or the prefix array, whatever you call. It will take big O of n into 26 time, where n was the size of str, n is the size of str, and m is the size of target. Then uh, for every L, we find out the leftmost R, or the smallest value of R, such that L2R is good. So for this, um, there will be n possible values of L. So big O of n time would be for that, like you will have n iterations for the different values of L. For finding out the R value, you can say that the binary search would be having big O of log n time, and in every, like inside the binary function, for every possible value of R which you encounter, you would call the function is good, which would in itself take big O of 26 time. So the binary search will overall take big O of 26 into log n time, and this is this n value. Yeah, we are having n possible values of L. So overall, this third step will take out big O of 26 into n log n time. So overall time complexity is big O of m plus big O of 26 into n plus big O of 26 into n log n. This 26 into n is insignificant in comparison to big O of 26 into n log n. So we can ignore this one. Overall time complexity is big O of m plus 26 into n log n. M would be less than equal to 1e4. So this is not really gonna cause a problem. It would be 1e4. This would be like 26 into 1e5 into log n of 1e5, that is 18. So our number of iterations, like this 1e4 is also insignificant in comparison to this. Now we are having around 468 into 1e5 iterations. This is around 4e7, or you like between 4e7 to 5e7, which is again good enough. This is uh, good enough to pass. It won't have any chances of TLE. So uh, I didn't do this just for calculating the time complexity, but for the revision as well. So you know about all the steps which we are about to do. Now I highly recommend you to try to implement the problem on your own now. Like implement this on your own. And I think the solution which I will show to you is gonna be clean. Like I think the code is clean enough. Okay, sorry, it's not clean. Earlier I had written a cleaner code, but uh, then it didn't work out, and I had made some changes, and it's not really bad though. Okay, there is one more thing. The problems which we solve with binary search plus prefix sum array, almost all the times these like this solution can be optimized by using dynamic sliding window. Almost all of the times they can be further optimized, but in our case, since this has worked out, we are going to implement this. And You will see that in the fourth problem, which is nothing but a follow problem of the third problem, the constraints are tight and this does not work out there. So we will have to optimize this to dynamic sliding window. But it won't be complicated. It would be very simple. Okay, so we have been calculating the prefix sum array, and since I don't like to write this thing again and again whenever I want to calculate the or want to find out the frequency of some character from L to R, I often create a function. I often create a function with name CNT, but you can feel free to ignore this and uh, at the place whenever you would have used the count function, you can just write free of. Okay, we want to find out the frequency from start to end, so free of m plus 1 I minus pre of start I. Feel free to write it like this, it's up to you. I do like to create a prefixum, a lambda function just after the prefixum arrays whenever I create them. After that, I'm having a count array that is target count, which we had been discussing the whole time. In the code, I had named it as rec, that is the required count. It is the short form of required count, rec. Um, and then I'm going up for each and every value of L. Okay, so in the code, I have named it as S, whereas in the explanation, it was L. So I'm calling it as S for now because it is in the code as S. So for each and every S, I'm finding out the uh, yeah, I'm finding out the first value of end for L, like for each L, or basically in the code I have written it as S. For each S, we are calculating, or basically we are finding out first value of E such that S2E is good. So this function will just tell me the endpoint. This is basically, you can call it as find E as well. For a given S, it will find out the E, but I named it as end here because in the function I had called it start. So here I am applying a binary search where for each and every M, like the binary search, I will have a mid value. So if this is the starting point, instead of naming R min, R max, and R mid, I'm having the names S, E, and M in the code. Though logically you can call them as R start, R max, R mid, or R end. So this RM tells that hey, if I take the string from start till this point, will it be good or not? I'm just checking this point, this part. So earlier I had actually written a good code. I had created a function with name auto is good, to which you will pass the start and end and the character index. And what it will do is it will go on for each and okay, sorry, you will just pass on the string and it will go for each and every character index by itself. So it will go like for char index from 0, char index till 26. um, the count of the string, the count of the character with char index, uh, this count from start, end, and char index should be greater than or equal to the requirement of that index. If this is greater than or equal to, then it is fine. Otherwise, just return false and at the end return true. So you could just directly call this function there. If is good start to end, we have created a function is good. So if from start till the mid, that is m, if this substring is good, then we will mark result equal to m for now, and we will try to search in this area now. So e will become equal to m minus 1, otherwise s will become equal to m plus 1, and we will search like this. And yeah, that's it. If like once we figure out the good endpoint, then we are just saying answer plus equal to n minus 1. And we have already discussed the time complexity. It was coming up as something like big O of m plus 26 into n plus 26 into n log n. So we could ignore this 26 into n, since it is insignificant in comparison to 26 into n log n, and that is the time complexity. Talking about the space, this is big O of um, n into 26 plus 26 time for, sorry, 26 space for this, which is insignificant. Uh, so yeah, the overall space complexity can be called as n into 26. In this case, both of these are good enough. But in the next problem, the memory limits, like in the fourth problem, the only difference is that the memory limits in this problem, the fourth problem, are smaller than usual, and the constraints for the length of n are a bit larger. So in that case, this will give us a memory limit exceeded error, and uh, I'm not sure if this we will get a TLE or not. Or yeah, actually we should get a TLE as well, because n would be as large as 1e6 in the next problem. So 1e6. Yeah, let me just write it on Excalibur. So n log n 26 into this. It would be 26 into 1e6 into log of 1e6 is around 20. So it is 520 into 1e6, which is 5e8, which is too much. So we should get a TLE as well. And if we try to create a prefix summary of 26 into n size, where n is 1e6, in general we can create it, but since they have been telling that the uh, memory constraints are even tight, like we are even having less space, so we can't create a prefix summary of this size. Now you might have a question that, bro, how will I know whether I can create a prefix summary of this size or not? So the answer is I don't know. I don't know. How would you know? In my case, what I did was I just tried to submit a solution with this much space complexity, and it gave me a memory limit exceeded. So I knew that, hey, I have to optimize it. So we do know one thing, but like I had told you about this earlier, that generally the problems which can be solved like this can be optimized to dynamic sliding window technique as well. So for the fourth problem, I had to optimize it to dynamic sliding window technique. Now, how will you know whether this can work or not? So the thing is, okay, let me first of all tell you about the difference between the two. The thing is, if for every L, when you were figuring out the R value, let's say for this L you got this R value, the smallest R value for which we got a good string, then for the next L value, when the value of L is incremented, can this R come up as any of these characters? Can this come up as any of these characters? The answer is no, because If when starting from this point, if you needed at least this much of a string to have a good substring, then obviously this substring might still be good, but any substring which is ending at a place early, like if there is any substring which is ending at a smaller value of r, it would definitely not, it would definitely be bad, right? Because if this was good, then this must have also been good, because we are adding a character. So we know one thing for sure, that as we increase the value of r, the value of r should also increase. Sorry, if we in as we increase the value of l, the value of r should also increase, or it can remain the same. It can remain the same or it will increase, right? Now when you know this thing, if this is true, if this is true and you can solve the problem with this method, then you can always solve the problem with dynamic sliding window as well. Almost always. um, there might be some complicated cases where it might be difficult or not possible with dynamic sliding window, though I'm not sure if there is any case where it is not possible. But I believe that most of the times whenever I have solved a problem with this method, almost always this thing also holds up, or probably this should always hold up, because mm, we were able to apply binary search here, and this method is almost always available. So in a nutshell, what I want to say is, if you solve a problem with this method and you want to optimize the solution a little bit, then you can think about the dynamic sliding window technique. It might be good for you in interviews. Generally, something like this does not happen much, that the memory constraints gets tighter and you fail to apply this technique. So now the thing is, what you can do. Oh yeah, by the way, this is a prerequisite. You should know about dynamic sliding window at least. Yeah, if you don't know how to solve this problem with dynamic sliding window, it is fine. But if you don't know how to solve a problem with dynamic sliding window, then you might have some struggle while attending the PCD. And I do highly recommend you to first of all learn about this and then come to this problem, then try it on your own, and then look at the tutorial if you fail. So now the deal is, I can maintain two pointers, L and R, and increase this value of R as long as, like, while and L and R is, like, while the substring from L to R is not good, increase R. So R will initially be here, but let's say that this L to R is not good, then you would have R here. Then let's say that this is also not good, then you will have it here. Let's say this is also not good, then you will have it here, then here. Let's say at some point of time you got that, hey, this L to R is good, then in that case you can, like, right now we were just uh, in the dynamic sliding window you have two things. You either grow the dynamic sliding window, you either grow the window or you shrink it, right? Some people call it as grow, some people call it as expand. So right now we were growing the window. Now when we know that this is a good string, good substring, so we can just add n minus r to the answer. Then we will shrink it a bit. So we will shrink this part by moving this L value here. Now check again whether L comma R is good or not. If it is good, if this is good, then again say n minus R, right? and again shrink it. So now what we are doing is while L comma R is good, we are adding n minus R to answer and we are incrementing L. And you need to make sure that L, like whenever you have L being greater than R, then the string is not good. The string L to L comma R is not good when L is greater than R, because this is not even a string. This is not even a substring when L is greater than R. So ठीक है. Now you can just do these two steps again and again. The way in which I like to implement the dynamic sliding window problems is I create a for loop in which I have L equal to 0, R equal to 0, and um, L is going up till n. L would be incremented, and then I have some while condition. Like in this case, it was that as long as R is less than n and is good for L comma R is false. Basically, L comma R is not good, then increment R. And when you have L comma R being good, in that case, increment the answer. That's it. And you know what? Um, oh yeah, one more thing. Since we would be removing this L just from the next term, like we are having this L plus plus here, we would be removing it. So uh, I can just remove the frequency now for the next iteration. So I can say that count of uh, strl should be decremented, and at the same time when I was adding this new character, I can just have a condition that hey, if R is less than n, basically the index is still on the string. In that case, count of strr should be incremented. This is how the code looks like. This is just my preference. If you want, you can have a preference, like you can code it like this thing and this thing. um Here, along with R plus plus and L plus plus, you will have to keep track of the count array. Now in case if we didn't have this uh, memory constraint to be smaller, then you could have still used the prefix sum array. You could have still used the prefix sum array, or basically the prefix arrays, but because of the memory constraint you can't create a prefix array, so you will have to keep track of the frequencies um, while sliding the window, while growing or shrinking the window, which is not a big deal. It's not a problem. So that's it for the problem. The time complexity, for the part of time complexity, you can see that this variable L and R, they will be incremented at most n times, right? Actually, they will be incremented exactly n times. Okay, I think I have been messing up with one thing. Uh, yeah, I could have here just said that hey, that yeah, it's fine. Like in this case, I have not added the constraint that um, if s is greater than e, then the string should be considered bad. I could have added this condition here like this, but it doesn't really matter, because as soon as s and d will become equal, your substring, like as soon as s will go above e, your substring would be empty. It won't have any characters. Basically, this count array would have all the frequencies to be 0. So automatically the uh, this condition will fail somewhere. That is why the code is not being affected. But it's up to you if you want to add one check that hey, L should be less than R. Okay, so here instead of naming it as check, you could have named it as is good. And we don't really need to pass L and R to the function because um, in the function you only care about the count and you already have the count vector containing all the frequencies, so you don't need to pass L and R. During the contest I had named it as check function. So for the part of frequencies, you are having L and R being incremented only n times. So you are having big O of n and big O of n time complexities for L and R. You are having a big O of m time complexity for calculating the target count array, and you are having uh, a big O of 26 time complexity every time. Uh, like every time this function is being called, it will have big O of 26 time complexity. It won't be called more than big of 2n times because the total number of iterations for this while loop would be uh, n. So yeah, the total time complexity can be set as big of 26 into n plus 26 into n plus m, something like this, which is big of 52 into n. N is less than equal to 1e6, so it is 52 into 1e6, that is 5e7, which is good enough. And the memory we are using is less than what we had used earlier. In fact, the memory is just this much. The extra memory which we are using is only this much. So yeah, let me show you the code. We are calculating the target count array. This is the target count array being named as rec here. And initially we are having we are having L equal to 0 and R equal to 0. So basically we have counted the first character in the sliding window initially, so that is why I added it outside. I added count of string 0 minus a to the count array. After that, I'm having this dynamic sliding window part where as long as e is less than n, the reason I have applied this is because at some point of time e will become equal to n. When e becomes equal to n by being incremented again and again, it means that now there are yeah, you can even add this here, but it's fine even if you don't write this line. As soon as okay, yeah, as soon as e becomes equal to n, every time you will just have answer plus equal to n minus n, that is 0, nothing would be changed. And otherwise if e is less than n, then we check if the string is not good right now. If it is not good, then we add a character like this. And yeah, we are making sure that e should be less than n while writing this line, otherwise you can get an error here because str of n would be invalid. And here we are doing the stringing part. Yeah, that's it for the problem. The time complexity and space complexities have been discussed. So that's it for this video. Thank you guys for watching the video, and see you all in the next video. Bye bye.